SwayamPrabha. Digital India. Educated India.
In this lecture, we are going to start with spatial kinetics of rigid bodies. To give you an overview, we are going to look at the equations of motion of rigid bodies in 3 dimensions. Now, we have already looked at these equations for planar kinetics in details. We have derived the equations of linear momentum and angular momentum. We are going to see what new thing comes up in the when we represent them in general 3D motion. We are going to look at the moment of inertia tensor. Then from these equations of motion, we are going to derive the work energy relations and the impulse momentum relations. Let us recall the equations of motion of a rigid body in which we write down the angular momentum equation about g. We have 2 equations. For the translational dynamics, we have the Newton's second law for the center of mass of the body, which essentially tells us that the rate of change of linear momentum of the center of mass is equal to the summation of all forces acting on the body, and this is the definition of linear momentum, which is mass, total mass of the body times velocity of the center of mass. This is for the translational dynamics part, and if you substitute this expression of the linear momentum vector, you get mass times acceleration of center of mass is equals to the force. This is for the situation when the mass of the body is constant. For rotational dynamics, we use this point g, the center of mass, and we have looked at this derivation. The rate of change of angular momentum about the center of mass must be equal to the net moment of all forces about the center of mass. How do we define angular momentum? This is how we define about center of mass. Rho is an arbitrary vector from the center of mass to an arbitrary particle shown here in the figure dm, and angular momentum is nothing but the moment of the linear momentum of this particle, and it so happens that when we do this for the center of mass, it is the relative velocity times the mass of the little element. This is the moment term cross relative velocity of the particle with respect to the center of mass times the mass measure dm. And for rigid bodies, rho dot, the relative velocity happens to be omega cross rho. This we have discussed many times in kinematics and kinetics. Using this vector algebra identity, we have in a previous lecture we have discussed how to express the angular momentum using only dot products. Therefore, we have a dot product between the vector rho times omega minus rho dot omega times rho vector, and that is integrated over the body. Let us look at this expression of angular momentum now. This expression is very simple to use. Rather than having cross products, having dot products is very easy to compute. In a general spatial situation, a spatial rigid body, we have the general vector rho as x I cap plus y j cap plus z k cap in some coordinate system which is fixed to the which is fixed up. We will qualify this coordinate system very soon. angular velocity of the body can be expressed again in this coordinate system as omega x I cap plus omega y j cap plus omega z k cap. Now, if I substitute these expressions of rho and omega, then I obtain this integral. This is rho dot rho times omega. Now, I have written as a column vector minus this is rho times, now this is rho dot omega. This is a straightforward calculation. If you combine this, if you do an algebraic step and simplify the whole expression, then this integral turns out to be integral of this matrix. And what I have done is I have pulled out the omega vector, which has nothing to do with this mass integral. Omega vector has nothing to do with this mass integral. This integral somehow measures the moment of the mass distribution. This is the second moment of mass distribution. Therefore, we have the angular momentum as integral of this matrix times this vector, this column, which is omega, and which I can pull out from here. In the first term, we already have this omega vector sitting here. This term can be written as x y z times omega x, omega y, omega z, and that is how I have pulled out omega from the second term as well. And what was left in the second term was x y z as a column, and therefore, what I would get is x square, x y, x z, y x, y square, y z, z x, z y, z square times omega x, omega y, omega z. And this matrix I have combined with this seems to be a scalar, but now since I am pulling out omega, this must be written as a matrix x square plus y square plus z square, here also x square plus y square plus z square, and the third term, in the third diagonal term, x square plus y square plus z square. Rest of them are all 0, and you can check that leads to the complete first term. Therefore, I have combined these two matrices, and this is our combined matrix. This integral is now represented in terms of these terms, which are called the moments of inertia and the products of inertia. I x x is nothing but integral of y square plus z square d m. This is the second moment of inertia, moment of inertia as it is called, and we have the products of inertia. Wherever unlike coefficients appear, they are called products of inertia. This is nothing but x y d m, and similarly I x z is integral of x z d m. These are therefore I x x, I y y, I z z, the terms which appear on the diagonal, they are the moments of inertia, and the off diagonal terms are the products of inertia. And this is written in a compact form, and this is known as the moment of inertia tensor, and you will notice that this is a symmetric matrix. As a matrix, this is a symmetric matrix, because I x y and I y x are the same, are equal. I x y is equal to I y x is equal to integral x y d m. Therefore, this is a symmetric matrix. If I can fix this frame to the body, then I also have time invariance of this tensor, of this matrix. That means, these terms I x x, I x y, etc., these will be constants if I fix the frame to the body. That simplifies calculations very much, as we will see. Therefore, from now on we will assume that this frame is fixed to the body. We will fix this frame to the body. This frame is called the body fixed frame or the body frame. Therefore, we will express our equations of motion, the moment of inertia tensor, everything in a body fixed frame to the extent possible. Not that in every problem we can fix it, but I mean that fixing the frame to the body simplifies the equations of motion, its representation, and the derivation of the equations of motion. Let us look at the next steps. So, this is our angular momentum about the center of mass h g vector. H g vector, the h g vector is nothing but the moment of inertia tensor about g times the omega vector. If you consider an arbitrary point P, you can calculate the moment of inertia, the angular momentum about P. You can calculate the angular momentum about P by adding to the angular momentum about G the angular momentum because of the motion of G. This also we have discussed many times before. Therefore, we have the angular momentum about G plus the moment of the linear momentum of G, the center of mass. This is P g is the momentum and capital G vector is the linear momentum of the center of mass, and linear momentum of center of mass is mass times velocity of center of mass. Okay, we come back to the translational dynamics. This is where we from where we started, and we had written the angular momentum equation or the rotational dynamics equation, and now we are going to express this rotational dynamics equation in the body fixed frame. And because it is now a body fixed frame, the frame itself will be rotating, and what will be the angular velocity of the frame? It is same as the angular velocity of the body. The angular velocity of the frame in a body fixed frame is same as the angular velocity of the body itself. Now, this is the equation of motion, the angular momentum equation. H g dot is m g. H g just now we have seen is equal to moment of inertia tensor times the angular velocity, and because we have chosen a body fixed frame, I g matrix is a constant, the tensor I g is a constant. Therefore, when I derivate this, because I am using a rotating frame, what is the frame angular velocity? Same as the body angular velocity. Therefore, d dt of angular momentum about center of mass is del del t of angular momentum about center of mass plus omega cross the angular momentum of the body about center of mass. This is our prescription for taking time derivative, and if you substitute this expression, in here, the local derivative, so which is not the derivative of the frame vectors, but the local derivative must differentiate this but I g is already constant, therefore, it will differentiate only omega, the coefficients of I cap, j cap, k cap in omega, and that I write as omega dot. This is the local time derivative. Then comes the frame derivative, and that is omega of the frame, which is same as omega of the body, cross angular momentum I g omega, and that must be equal to the net moment about the center of mass, and I g has been expressed again, written out here again. We can have some simplifications are possible if we choose the frame xyz frame, which is of course fixed to the body, it is fixed to the body. If I choose in a very special way, if I choose the frame axis as the principal axis of the body. Now, these things you must have studied in mechanics. What are principal axis of a body? The principal axis of a body are is the frame in which the moment of inertia tensor is completely diagonal. The moment of inertia tensor about g is completely diagonal in the principal body fixed frame, and this simplifies the whole equation. Therefore, the moment of the angular momentum expression, which is I g times omega, becomes very simple, I x x omega x I cap plus I y y omega y j cap plus I z z omega z k cap. This becomes extremely simple. This is the angular momentum, this is h g vector. Now, with that, if you substitute in the equation of motion, if you substitute in here, then these terms are born out of the first term because of the local derivative I x x times omega x dot, that you can see from here also. It is time derivative of this in the I cap, this is the I cap equation, this is the j cap equation, and this is the k cap equation. In the I cap equation, I have temporal derivative, local derivative of this term, I x x is constant, therefore, omega x dot, and from this cross product we have these terms in j and k. This equation is known as the Euler's equation for rotation. This is known as the Euler's equation. Therefore, what is Euler's equation? Euler's equation is the equation of rotational dynamics of a rigid body written in the principal body fixed frame, in the principal body fixed frame. And you can remember this equation very easily, it is I x s omega x dot minus, now there is a difference between I y y I z z and product of omega y and omega z, and that is m g x, and this pattern is repeated in all the other equations. We have therefore, the translational dynamics for now using a point O, which is a fixed point in inertial space, and this body is rotating with this point fixed. Translational dynamics is written in the same way, only thing you have to remember is this force, net force, must include the reaction force at the support point O. Therefore, F includes the support reactions at O. Rotational dynamics I can write as h naught dot is equals to m naught, this we have seen before. This is a point, O is a point which is fixed in inertial space, therefore, I have this simple angular momentum equation. The rate of change of angular momentum about O must be equal to moment of all forces about O. Just like we derived the moment of inertia tensor about G, we can also define the moment of inertia tensor about point O. And for this you can use the axis theorems for shifting the point. and if I fix the axis, the coordinate frame to the body, then I naught is a constant, and the rate of change of angular momentum about O is the local rate of change of angular momentum about O plus omega cross the angular momentum about O vector. And therefore, from these expressions I can find this equation. This is the rotational dynamics equation for a body rotating about a fixed point. Note, you should remember that when we discussed kinematics of an axisymmetric body rotating about a fixed point, you should remember that the frame that we used was not a body fixed frame. It was not a body fixed frame. The frame was defined in a certain way, and the angular velocity of the frame was also determined, and that was not equal to the angular velocity of the body. We will look at axisymmetric bodies which are rotating about a fixed point in a moment. Now, we had discussed about this fixed axis rotation, or what is also known as parallel plane motion. Why it is called parallel plane motion? Because any points of this rigid body, all points of this rigid body are moving in parallel planes. There is a fixed axis. If you consider a body fixed frame as I have shown here, then we can write down the equations of motion for this body. Mass times acceleration of center of mass, I have shown the center of mass, it is arbitrarily placed, need not necessarily be on the axis of rotation, and that is equal to the net force on the body, which includes the support reaction forces. And we have the rotational dynamics equation, which is essentially the angular momentum equation, which we have just now derived. In this case, we have this restriction that the omega vector is along the z cap direction or the z axis. I have chosen the frame in such a way that the omega, the angular velocity, is along the z axis. Therefore, omega vector must be 0 0 omega z, or in other words omega z k cap. This is omega z k cap. And the general representation of the moment of inertia tensor is this, which we have seen before, and therefore, because of this simplification in the structure of omega, angular velocity of the body, we can write down the Euler's equation in a more simpler form, and this is the form that we obtain. Of course, the Euler's equation was for written for the principal body fixed frame, but this may not be a principal body fixed frame. Therefore, these equations are slightly different. Here you will note that we have these three equations, and in the first two equations, because omega x and omega y are 0, there is no question of rate of change of those. Therefore, no angular acceleration term appears in the first two equations. Only in the third equation we have the angular acceleration about z, omega z dot. And this reminds us, the third equation should be reminding you of the planar kinetics equation, rotational dynamics equation that we used in planar kinetics of rigid bodies, and there we impose this restriction that we were discussing for prismatic bodies. Why? That reason should now become clear. Even though this is a fixed axis rotation, this is not a planar kinetics problem. The reason being the first two equations, the x I cap and j cap equations. Because of these two equations, this system is not a planar kinetics problem. This body is not under planar kinetics, but it can reduce to planar kinetics. Under what conditions it can reduce to planar kinetics? it can reduce to planar kinetics if z is a principal axis and xy plane contains g. Remember, we always said this while discussing planar kinetics, that g must be contained in that xy plane. And now we have this additional requirement that z is a principal axis, because when we have this, then these terms will vanish, these terms will vanish, and when these terms vanish, these go to 0, and then we are left with only this equation. Therefore, for planar kinetics for a general rigid body motion with fixed axis, to reduce it to planar kinetics equation, z must be the principal axis and xy plane must contain g, the center of mass. These are some moments of inertia terms for regular bodies, which you already know. This is just a recapitulation for a cylinder, for a block, for a sphere, the simplest, and for a slender rod. For a slender rod, you will notice what is the difference between a cylinder and a slender rod is that Izz here is 0, though it will never be actually 0 in any realistic situations, but this is negligible. What we will say is this is negligible. Now, from the equations of motion, let us see the work energy relations. The way to derive remains standard, this we have discussed before. We dot product the translational dynamics equation, the Newton's second law for the center of mass, we dot product it with the velocity of center of mass, and we dot product the rotational dynamics equation with angular velocity. And if you sum up, then you will get the grand equation for work energy relation. This is of course in derivative form. You can identify the terms, the translational kinetic energy and the rotational kinetic energy, and from here you will find what is rotational kinetic energy, half omega dot Ig times omega. Translational kinetic energy is straightforward, it has been discussed before, and on the right hand side we have the power input or power exchange of the system. One thing you may note that this Ig being symmetric, the moment of inertia tensor being symmetric, therefore, omega dot Ig omega, which is the angular momentum about g, is equal to omega dot Ig omega dot. This is because Ig is a symmetric tensor. Therefore, I can pull out d dt. I can pull out d dt because of this property. I can pull out d dt. This you should check. Why? Because when I do the d dt of this term, I will get once this term, another time this term, and that makes it 2 times, and that is how I will actually get this. Therefore, so that I have used in pulling out d dt from here. One thing you should note that this term which is omega cross Hg dot omega, this must be 0. Why? Because omega cross Hg must be perpendicular to both omega and Hg. What is important is it is perpendicular to omega, therefore, something perpendicular to omega dot omega must be 0, therefore, that term drops out. Thus, our kinetic energy expression is written in terms of now linear momentum and angular momentum. This I have shown here, I have expressed it now in terms of linear momentum. This is linear momentum of center of mass, and this is angular momentum about the center of mass, and that is what I have used, the kinetic energy of the body. And if you have kinetic energy using a fixed point or point that is instantaneously at rest, not just a fixed point, but maybe a point instantaneously at rest, then you can simplify the kinetic energy expression. How? Because V g can be written as V o, that fixed point instantaneously at rest, or the point about which this is rotating, V o is 0, and that plus omega cross this vector r g, this vector r g, omega cross r g, because V naught is 0, V g is omega cross r g, and therefore, we can write kinetic energy in this form. Here I once again use, so V g is omega cross r g, this term, dot g, this is scalar triple product, therefore, I can make a cyclic permutation that remains constant. When I do that, this I do to pull out omega. Here there is a correction, there is no omega dot, this is a correction. Therefore, I can now pull out the omega from this term. I can, this term becomes r g cross g dot omega, and this term is omega dot h g, of course, 1/2 is there, and therefore, I can pull out omega dot, and what remains in the brackets is r g cross g plus h g, but this you know is nothing but the angular momentum about the point O. Therefore, the total kinetic energy is equal to 1/2 angular velocity dot angular momentum about O, with O is the point which is instantaneously at rest or the point about which the body is rotating. And we have this decomposition, the rate of change of kinetic energy of translation and rate of change of kinetic energy of rotation in terms of the power exchange. Now, if you integrate over time, you will get the change in kinetic energy of the body between two time states as the net impulse generated by the force and the moment. The change in the translational kinetic energy comes from the integral of force dot velocity of center of mass over time, and the change in the rotational kinetic energy comes from the integral of the moment dot omega vector over time. Now, the impulse momentum relations, these are straightforward. We have about g the equations. The first is of course common to all, the linear momentum equation, which is Newton's second law for the center of mass, and the second is written for the center of mass, the angular momentum equation about the center of mass. If I just integrate over time, I get the change of linear momentum of the center of mass is equal to the linear impulse, the impulse of the force, net force that is acting on the body, which is integral of f dt, and the change in the angular momentum of the body about the center of mass is the integral of the moment, which is the angular impulse. The integral, time integral of the net moment acting on the body is the angular impulse. And note that the moment can also include couple moments. So, that gives us the impulse momentum relations for the rigid body. Just to summarize, we have looked at the equations of motion of a rigid body in 3 dimensions. We have derived the expression for the moment of inertia tensor, and We have looked at some standard shapes and I hope that you have studied moment of inertia in your course in mechanics. We have looked at the work energy relations and the impulse momentum relations. With that, I will close this lecture.